Tea Time Talks. We are happy to have you here. We are part of Interpore Young Academy and we want to talk about the porous media and boost the science among young scientists. I am Nara Brandão from the Federal University of Uberlândia in Brazil and I will be your host today. I have Mohammed from the University of Oslo in the studio with me. Please feel free to subscribe to our channel and receive notifications from us. Today, we are going to have two great presentations from Eddie and Ramin. At the end of each presentation, we are going to have 5 minutes for question and answers, and you can participate by typing in your questions and comments in the chat box on the right-hand side. So, let's start. Our first speaker is Eddie. He's a PhD researcher from Imperial College London. He will talk about the identification of the leading role of pore structure in determining recovery during low salinity water flooding. So, Eddie, you are welcome and the floor is yours.
Thank you, Nara. Yeah, hi everyone. My name is Ed, and as Nara said, I'm a fourth year PhD student at Imperial College London. And today I'll be talking about my work looking at the role of pore structure in recovery during low salinity water flooding. So I'll start with a very brief overview of low salinity water flooding. It's an enhanced oil recovery technique, simply where low salinity brine is injected into a target reservoir, and that can either be as a secondary or tertiary water flood. Now, it's generally accepted that a wettability alteration towards a more water wetting state is the primary driver for improved recovery during low salinity water flooding where it is observed. However, one of the uncertainties surrounding low salinity flooding is really understanding exactly which systems will respond well to the technique and which systems will not. And part of this uncertainty comes from the fact that it's still not exactly clear how kind of this wettability alteration on the small scale, so for example, experiments on flat surfaces, really equates to recovery over larger scales, so over core and field scales. And really to kind of break down this kind of barrier and to really fill this gap across scales, we need more Pore-scale observations. Now, just like with lots of fields in kind of multi-phase flow, X-ray micro CT imaging has been really powerful in the last decade or so for low salinity flooding, and there's been some really amazing observations, Pore-scale observations of contact angle distributions and pore occupancy, and direct observations of fluid occupancy in all sorts of experiments over the last decade. However, in sandstones, these Pore-scale observations have been limited just to Berea sandstones. And what that means is that it's really difficult to understand exactly how, say, pore structure and mineralogy impact oil mobilization and recovery, because we just have these Pore-scale observations on a very small set of samples. So today, the goal is to kind of look at Pore-scale observations over a range of sandstone samples. So I've carried out experiments over Berea, Bunter, and Castlegate sandstones. And these are sandstones with similar mineralogies, but quite different pore structures. And we'll go into that in more detail. And the idea of this is to really try and understand exactly how this pore structure facilitates oil mobilization and the role it has to play in recovery during low salinity flooding. So as I said, we've got these 3 different samples, so Berea, Castlegate, and Bunter. I'm going to talk very briefly about them now. So the experiments were carried out on tiny little cores, so 20 millimeters in length and about 6 millimeters in diameter. Here we have a dry scan of each of the cores, so Berea, Bunter, and Castlegate, where we have also the segmented images where black is the pore space, yellow with clay minerals, and then the turquoisey color is all the non-clay minerals. So we can see we have a significant clay fraction in each of the samples. But what we can see is that the porosity and permeability values vary quite a lot between the samples. We are seeing quite a different pore structure, and there are other ways the pore structure varies as well, and we'll go into that in more detail. But what we can see is there are similar clay contents, which is important for low salinity flooding. So in terms of the experiments, we took each of these cores, we carried the exact same experimental workflow out for each of the cores. So we first of all injected a high salinity brine, followed by an undoped crude oil. Then we aged all the samples, which meant that we submerged the samples in oil for 4 weeks at 80 degrees C, and this was so that the samples went to a more oil wetting state. Then after the aging process, we displaced the undoped crude oil with a doped crude oil containing iododecane. The reason for that was so that we could get contrast between the brine and the oil. And then we carried out the water floods. So a secondary high salinity water flood for 12 pore volumes, followed by 2 tertiary low salinity water floods for a total of 20 pore volumes injected. And after the steps 3 to 7, we imaged the cores with an X-ray micro CT scanner, and we attained a resolution of about 2.4 microns. So I'll jump straight into the results now. And first of all, talk about the saturation changes within each of the samples. So here are the saturation profiles. So on the x-axis for each sample, we have the water saturation. On the y, we just have distance from the inlet. So for each of these cases, we're injecting from the bottom here. If we focus first of all on the blue line, so this is after high salinity flooding, we can see that there's quite a variation in saturation throughout all of the samples. And this is kind of expected when it comes to an oil wet system. You expect a kind of heterogeneous distribution of water saturation. What's interesting is then when we have our tertiary low salinity water flood, in the Pore and the Bunter particularly, we're seeing quite a complex redistribution of fluids. It's not as though the saturation is moving just in one direction. We're seeing this kind of complex redistribution, and that's really interesting. But really the main takeaway from this slide is the recoveries. So we see in the Pore and the Bunter samples that there's an additional recovery during low salinity flooding of 3 and 4 percentage points, whereas in the Castlegate, we're seeing a lower recovery of about 1 percentage point. Now we can kind of break up this oil recovery during low salinity flooding into kind of 2 factors. One of those factors is how much oil is actually mobilized during low salinity flooding, and the second is how much of that mobilized oil is actually produced. And today I'll focus more on this oil mobilization. So that's this left-hand column here. So these numbers are simply the oil that was in place after high salinity water flooding. What fraction of that oil was then mobilized or displaced during tertiary low salinity flooding? And we can see for the Pore and the Bunter, it's a very large percentage. So about a fifth of all of the oil that was in place after high salinity flooding is actually displaced during low salinity flooding. The value is about half of that for the Castlegate. So there's quite a big disparity, and this really is the root of where the difference in recovery factors come from. But now we have to ask ourselves, okay, we have these samples which all have similar mineralogy, and we carried out an identical experimental workflow on each one. So why do we get these different responses? And today I'll be talking about the role of pore topology or pore structure, but more specifically pore topology. And in particular, the role of the largest pores and the connectivity of the largest pores. Now I'll go into more detail about why these large pores are believed to be important in a few slides' time. But first of all, I just want to highlight the differences in the connectivity of these large pores. So what I've done here is I've extracted a pore network for each of the 3 samples. And then I've just isolated the largest pores, which make up 60% of the pore volume. So just the largest pores in each sample. And then I've plotted them as a volume rendering, and I've labeled the images so that each kind of different color is a connected cluster of large pores. So what that means, for example, in the Castlegate, what we see there is we have one kind of color, one cluster all the way through the region of interest. So that means these large pores are very well connected. And that's not the story at all in the Pore, where we have kind of very fragmented clusters. And that means that the large pores are very poorly connected in the Pore. And in the Bunter, interestingly, we have this kind of tale of 2 halves. So in the upper part of the Pore, we have a relatively well-connected pathway of large pores. And in the lower section, we have the opposite, more of a Pore type behavior, where we have the large pores are poorly connected. Now, this has some significant impacts on the brine distribution in each case. So if we look, for example, in the Castlegate sample, where the large pores are really well connected, we see that brine is able to connect across these large pores after high salinity flooding. So what I've plotted here is the largest 3 brine blobs after high salinity flooding in each case. And as I said, in the Castlegate, we see that the largest brine blob kind of connects across the sample after high salinity flooding in the Castlegate. And to really understand why this is the case and the implications for this after high salinity and then subsequent low salinity water flooding, I'm just going to very quickly run through an idealized kind of pore network model, just to really try and make it clear what's really going on here, why pore topology is so important. So first of all, I'll go through an example where we have this pore network where the pores are these circles, and then we have throats of these kind of sticks connecting the pores. And this is a a case similar to the castle gate, where the largest pores are well connected. So we see there's a nice pathway of large pores that can kind of connect across the sample, just like we see in the castle gate. So we're going to saturate this pore network with oil, and then we're going to go ahead with a high salinity water flood. Now, because the large pores are well connected, because it's a drainage regime where we're injecting brine into an oil wet system, the brine will preferentially want to flow through the largest pores. So we get this invasion percolation type pattern where brine is invading the large pores preferentially. Because they're well connected, we can simply connect across the sample at a relatively low absolute magnitude of capillary pressure. And that's fine, that's what we'd expect. And this is a very stable pathway of brine. And this is what we see in the castle gate. And that's why we have this kind of large brine cluster spanning the region of interest in the castle gate. But if we just subtly change the pore network so that now we've got some local constrictions. So for example, some pores and throats get a little bit smaller, the large pores are now more poorly connected. If we go ahead with a high salinity flooding of the same magnitude of capillary pressure, we find that we can't span the network. And that's because we reach these kind of local restrictions where the entry pressure to the smaller pores and throats is a lot higher. So what happens then is we keep injecting until we reach this kind of threshold capillary pressure, and we can invade some of the pores and the throats, and we can then span the network. So that's all fine. But what can happen then is that we get these Haynes jumps. So we span these kind of local constrictions, and then with the given capillary pressure, we can then invade a whole cluster of large pores. But what that does, it makes these areas where the brine is occupying the smallest pores and throats, makes those areas extremely unstable. And what can actually happen then is you can get local and distal snap-off events. So oil snap-off, where due to a drop in capillary pressure after Haynes jumps, you can actually get oil kind of displacing brine in the smallest regions, and that acts to break up the brine cluster. And this has been observed experimentally in synchrotron imaging in this great paper looking at just a two-phase flow problem in synchrotron imaging, and you can really see that oil snap-off events can really break up this brine cluster. And that's what we think is going on in the Berea and Bunter samples. So that's why the brine maybe isn't kind of spanning the network after high salinity flooding, because it's broken up. But so far we've talked about just high salinity flooding. But what are the connotations then? What happens during low salinity water flooding? So if we have this case on the right-hand side, for example, so this is similar to the castle gate sample, where we have the large pores that are well connected. If we go ahead now with a tertiary low salinity water flood, the low salinity brine can happily just span the network in the pre-existing pathway that high salinity brine has created. It's not desirable or preferable for the brine to go ahead and start invading small pores and throats, because it can simply just flow along the existing pathway of high salinity brine. So that acts like what you'd imagine is a typical tertiary water flood. However, if you get this system where we have the large pores are poorly connected, when you go ahead with a tertiary low salinity water flood, it acts in a way more like a secondary flood, where now for the brine to span the network, it has to displace oil. Oil has to be mobilized so that the low salinity brine can span the network. And this, we think, is the root cause of why oil mobilization is higher in the Berea and the Bunter samples. And what's really cool is we can actually see this happening locally in the Bunter sample. So as I said, it's a tale of two halves. So in the top half of the Bunter sample, we see that the large pores are really well connected. In the lower half, they're more poorly connected, similar to the Berea sample. And what we see is actually in the top half of the core, where the large pores are well connected, we see there's not much recovery. So this is actually about a 1 percentage point additional recovery in the top half of the core, and in the lower half we get about 6 percentage point additional recovery. So where the large pores are poorly connected, there's much more oil mobilization. And we can also see that the brine distribution acts exactly as we'd expect. So the largest three brine blobs after both high and low salinity flooding are all in this top half, where the largest pores are well connected. So it really seems like the topology of these large pores really has an impact on the brine distribution and indeed recovery and mobilization of oil during low salinity water flooding. So I'll just wrap up there and say that this work is explored Pore-scale results from 3 different sandstone samples, and we saw there was really great, really strong recovery in the Bunter and Pore samples of 3 and 4 additional percentage points. But we found that pore structure was really important, in particular the connectivity of the largest pores. So in essence, when you get these well-connected large pores, it makes oil mobilization less favorable, and therefore you get the lower recovery during low salinity flooding. Now, this is just the start, really, of this work. It's really highlighting the fact that pore structure can be really powerful when it comes to low salinity flooding, but more work needs to be done to really explore this further. So it would be great to see some pore network modeling to carry out a sensitivity analysis to see different aspects of pore structure. Maybe aspect ratio has a really big part to play, for example, pore scale disorder. So it'd be really, really interesting to see a sensitivity analysis. And the kind of ultimate goal of this work is to build a screening criteria so we can better understand, okay, this rock has a pore structure which predisposes it to a positive low salinity response. That would be a really, really powerful tool. So yeah, that's the end goal. So with that, I just want to say a quick thank you to my sponsors, EPSLC and BP, and say thank you very much for listening, and I'm more than happy to answer any questions. Thank you.
Okay, so thanks, Eddie, for your great talk. And I'm very interested in this topic, so I really appreciate your presentation. And now we are going to have some question and answer sessions, and please feel free to type your questions on the chat box, and then I can read that to Eddie. And see, we have one here. Let me open my screen and put it here. So it's from Mojtaba. Thanks for your talk. Do you think in such experiment a time scale and for which wettability alteration takes effect should be considered for the run time of the experiment?
Yes, that's a really great question. I think there's still a bit of uncertainty as to exactly what the timescales of a wettability alteration are during low salinity flooding. What I will say is that for these experiments, that the flow was carried out over kind of 8 or 10 hours at a time because the flow rates we used were very low, 0.015 mil a minute, just so we could ensure that it was a capillary dominated regime. We did see a wettability alteration in both the Berea and the Bunter samples, and that was measured using a fluid coated area fraction measure. So we did see that the production was linked to wettability alteration. So we do believe that there was enough time for a wettability alteration to take effect. Whether that was enough time for the kind of ultimate wettability alteration to take effect, we're not entirely sure, but there was definitely an alteration. But with this work, the interplay between a wettability alteration and the pore structure is a little bit complex, because a wettability alteration is also linked to clay content and exactly where the clays are in the sample. So, for example, in the Castlegate sample, we find that the clays are in the smallest pores, and the brine almost never touches the small pores. So there's very little opportunity for a wettability alteration, no matter what the time scale is, because the brine is just preferentially flowing through a pathway of high salinity brine, or a pathway that's created by high salinity brine. There, we don't really see a wettability alteration, and we think that's not because of the time scale, but rather because there was just no opportunity for the brine to come into contact with many oil saturated pores or oil coated surfaces.
Okay, great. And now we have another question from Martin Platt that I can share with you. Please, can you comment on the role of topology of carbonates with a wide range of pore size? Does this make it favorable target for LSW?
Yeah. That's a really interesting question. I hadn't thought about that. So I guess one of the major differences between a sandstone and a carbonate is the presence of microporosity in carbonates. So I think if we were to look at this work, if for a carbonate which had say as much as a wide range of pore sizes, that means potentially the largest pores are not well connected, then I would think that yes, that would maybe make them preferable over sandstones if the sandstone has kind of a more connected pathway of large pores as we see in the Castlegate. So yeah, wherever there's a sample, whether it's a carbonate or a sandstone with this wide range of pore sizes, that's potentially preferable for low salinity water flooding. I think one caveat to that is there's still some uncertainty about because the mechanisms for low salinity flooding are slightly different between sandstones and carbonates. I think the common ground there is a wettability alteration towards more water wetting conditions as the primary driver for recovery. So I'm not entirely sure if the slightly different mechanisms would affect response, but yeah, I think in short, potentially this wide range of pore sizes would be preferable because we're not getting the same pathway of connected large pores.
Okay, great. And so here, and meanwhile, I also have a curiosity from my side. And please, you talked about injection of water with low salinity. And so, do you expect a different behavior if you injected water with different salinity? So, concentration of salt, yeah.
Okay, so you mean if we injected a higher salinity brine?
Yeah.
Yeah, so I didn't. So what we saw? Yeah, that's a good question. I think still the low salinity brine is really integral to the recovery that we see because so if we go back to, if I just flick back a few slides to the pore network models. So still we are seeing that a wettability alteration is really integral to the recovery, and we think that wettability alteration ultimately comes from the fact that there's low salinity brine present. But what's really interesting is, so for example, in this scenario where we have brine that has to kind of mobilize oil as it flows through the sample, because when the low salinity brine can come into contact with an oil-coated surface, it can alter the wetting state. What you can end up with is permanent pore occupancy changes, where suddenly, because the local wetting state changes when we invade these restrictions, there's not the tendency for the oil to snap off again into that pore. So you get a more connected brine network, and so then you get the more permanent pore occupancy changes and more permanent kind of mobilization and distribution of oil. So we think that the low salinity brine and the wettability alteration is still integral to the recovery. So therefore, low salinity brine is going to be needed for this. But the real question here is, has the low salinity brine got the opportunity to alter the wetting state and got the opportunity to mobilize the oil in the first place? So in the Castlegate, even though the clays, for example, could be very reactive, in the Castlegate, the brine just simply doesn't have the opportunity to alter the wetting state because it's just flowing along a preferential pathway. So the low salinity brine is really important if it can alter the wetting state. So that's the kind of, so if we injected high salinity brine, then I don't think we'd see the same response.
Okay, yes, I got it. Thanks. Okay, so I guess we don't have other questions from the audience, and I mean finally from my side, and so maybe we can move to the second speaker. Yeah. Okay. Oh, just a second. Sorry, we got another one for you, Adi. Just a second,
sure.
please.
Yeah.
Yes. It's here from Sina. Thanks for the talk. How do you differentiate between mobilized fraction and produced fraction?
Yeah, so when we look at the mobilization of oil, we literally take the segmented images of the fluid distribution after high and low salinity flooding, and we just look for any areas where there was oil and now there's brine. So any area where brine has displaced oil. But that's a very different question to how much oil is actually produced, because then what we look at is that there's that volume, so the volume of oil that's actually displaced, and then we also look at the total volume of oil that's left to core, so the volume that's actually produced, and that's how we distinguish between the two, and then we can find a fraction of the mobilized oil that's actually produced. So that's the distinguishing factor.
Okay, great, thanks. Okay, so now I guess you're ready. And thanks again, Eddie. We appreciate your talk.
Thank you very much. Thank you.
Thank you. And now our second speaker is Ramin.
Yes, hello.
I have his introduction here. Just a second.
Just let me know if you see my presentation because I can't see you at the same time. So
Okay, yes, we can see your presentation. Let me see. Yes, it's fine. Okay, so I guess Mohammed will introduce you, please.
Thank you, Edward, for the wonderful talk. And now we can move on to the next presentation. Our second presenter for today is Ramin Moghadasi. Ramin is a PhD student at the Uppsala University in Sweden and also in Imperial College London. He's working on geological CO2 storage in deep saline aquifers, focusing on residual trapping of a range of scales. In his work, he has investigated the role of gas remobilization, characterized by critical saturation in interpretation of a field-scale CO2 experiment. Ramin also conducts Pore-scale Pore-scale and pore network modeling to study the relevant Pore-scale physics of the residual gas remobilization. Thank you, Ramin, for joining us today, and the floor is yours.
yeah, thank you very much, everyone. Hello. I'm so delighted to be here on this talk today. So I'm going to talk about part of my PhD project, which is on determining gas remobilization and critical saturation in the context of CO2 storage, specifically with the evidences from field scale, and also I will talk about the Pore-scale mechanisms to the end. But before I start, I would acknowledge my colleagues, both from Uppsala University and Imperial College and other institutions, which really helped me out with this work. So the outline of my talk is as follows. First of all, I will talk about the background of residual trapping to understand what the residual trapping is indeed. And then I will talk about the field observations, the field experiments that our group conducted in 2017 and 2016. And then I will go through the theory of gas immobilization, and then I will show the model, results, and then conclusions. So first of all, we all know that we are kind of facing these climate changes in terms of the global temperature rise. And geological CO2 storage is one of the methods to mitigate the climate changes by capturing the atmospheric CO2 and injecting it deep underground, like 1 or 2 kilometers deep, potentially into saline aquifers and depleted oil and gas reservoirs. When the CO2 reaches at that depth, several mechanisms come into act to keep the CO2 stored for many, many years, which are called trapping mechanisms. And if we look to the right-hand side figure, we would understand that residual trapping specifically is giving a significant contribution to the overall trapping among the other trapping mechanisms. And that's why in my project, we are focused on the residual trapping as most. And also residual trapping is known as a key mechanism in geological CO2 storage. So to understand what the residual trapping is, let's assume that we have an aquifer to which the CO2 has been injected, and now the CO2 injection has been stopped. So what happens is that the supercritical CO2 moves upward due to buoyancy, because CO2 is obviously lighter than saline brine. So we have a buoyant movement, and at the tail of the CO2 plume, what happens is that the brine will imbibe back and will occupy some of the pore spaces which are now filled with CO2. And as a result, and due to capillary forces, some of the CO2 will be trapped, and we will have this residual zone at the tail of the plume. And at the same time, of course, we will have some dissolution trapping because the CO2 is soluble in brine. So if we look at to this this region a bit more closely from Pore-scale perspective, we would have a kind of distribution like this. It's not the perfect one, but yeah. So we would have these trapped bubbles of CO2, which are really kept there by capillary forces, and mainly due to snap-off. As you can see here, for instance, here it is kind of, I don't know if you see my pointer or not, but as a snap-off is just about to take place. But looking at this phenomena from a macro scale perspective, what we would see is that during the injection, we would have the CO2 saturation, which is increasing, the red curve. And at the end of injection, or if you just look at the tail of the CO2 plume, we would have a CO2 saturation, which is decreasing, and so does the CO2 mobility. And at some point, we will reach at a point where the CO2 saturation is not zero, but the CO2 mobility is effectively zero. And that saturation is called residual saturation. And it is noted by SGR and is actually used to quantitatively characterize the residual trapping. But now let's assume a scenario in which the pressure declines. It might be due to a leakage from the wellbore. It may be just simply because of pressure dissipation near the wellbore, or maybe a fracture happens, in many years, and then we would definitely have some pressure depletion in the reservoir. So what happens is that, first of all, some of the CO2, some of the trapped CO2 will expand, because the CO2 is a compressible fluid. And at the same time, some of the CO2 which were dissolved in the aqueous phase will now exsolve, right? Because the CO2 solubility is a function of pressure. So both these two mechanisms together increase the CO2 saturation. And if we look at the CO2 mobility against CO2 saturation, what we would expect is that the CO2 at some point should become mobile because the CO2 saturation is really increasing, and so does the CO2. So should the CO2 mobility. And that is the definition of critical saturation in the context of CO2 storage. This is actually the saturation at which the trapped CO2 becomes mobile again. But now the question is that when it gets mobile, and if it gets mobile, how does it behave? That's the question we want to investigate. We would also have this term, which is the difference between critical saturation and residual saturation, which is noted by SG mob or mobilization threshold. But in this case, we have some evidence from the field scale experiments that our group conducted at Hellet's site in 2017 and 2016, which is a scientifically motivated CO2 injection experiment, and indeed is one of the few pilot-sized CO2 injection experiments worldwide in which 50 tons of CO2 was injected. This is to the right-hand side, this site map, and I highly recommend reading this paper here, which details out everything about the CO2 injection experiments at the Hellet site. So basically, what we did at the Hellet site to characterize the residual trapping and also determine the residual saturation and also characterize the critical or gas remobilization and then determine the critical saturation was like this, that we have before and after. So we do a couple of tests like hydraulic, thermal, and tracer tests just before creating the residual trapped zone. And we do the same experiments just after creating the residual zone of CO2, which can be established either by pushing the CO2 plume with more brine or just letting the well open to the atmosphere so everything that is producible is produced, and then we would have the residually trapped zone. But at the Hellet's injection experiments, we did both indeed. So we pushed the CO2 plume with brine, and also we let the well open to the atmosphere, so we would have both effects from the So by having the results from this before and after, before creating the residual zone and after creating the residual zone, we can characterize the residual trapping in situ and actually measure the residual saturation. So we did that, and the only way that we were able to get a good match with our field data and tracer data was to take the critical saturation into account. If you look at the right-hand side figure, you can see here that if we do not take the critical gas saturation or the phenomenon of gas immobilization into account, we would not be able to capture the second peak of field data. But as soon as we implemented the phenomenon of gas immobilization into ITOF2, we were able to indeed capture the second peak, even though we tried before taking the critical gas saturation into account, we tried lots of scenarios like heterogeneity, different well-parent curves, and everything that we tried. None of them worked. But indeed, the critical gas saturation was determined to be the reason. So we have field scale evidences that we would see gas mobilization, trapped gas mobilization in the context of CO2 storage. Now we want to explore this phenomena a bit with the Pore-scale, at the Pore-scale, because everything is happening at the Pore-scale, right? The capillary forces are active at the Pore-scale. Residual trapping is actually, taking place by the capillary forces. So we have to look into what is really happening at the Pore-scale as well. So the Pore-scale mechanism, first of all, we would have gas diffusion. As the pressure is depleting, we would have the exsolution, right, from aqueous phase to the gas phase, and also from pore to pore and across the aqueous phase, which can be calculated using the fixed first law. For instance, here it's a simple structure of the pore space, just for the demonstration purposes. That if we have a concentration difference, we would have a concentration gradient, and that actually leads to a mass flux between two pores. And so we have to model the gas diffusion first of all. And also another phenomenon which we have recently added into the code is the Ostwald ripening, which is also driven by the molecular diffusion. But indeed, the differences in capillary pressure is what's called the Ostwald ripening, is actually driving the Ostwald ripening. So if we have two pores, which the concentration is the same in two pores, but the capillary pressure is different, then still we would have some mass flux between these two pores due to capillary pressure until we reach the capillary equilibrium. So the gas diffusion is divided into these mechanisms, and then we also have the gas growth. So as the pressure is declining, we would have mass, which is, of course, gas, is being added to the trapped gas phases, right? So the pressure increases. Also, we have the expansion of the gas phase, both leading to internal gas pressure increase. And as soon as we meet this criteria here, we would have an invasion. So the gas clusters grow in size, and eventually they may get connected and merge together, and we would have a flow of trapped gas. So these are simply the Pore-scale mechanisms behind the gas immobilization in the context of CO2 storage. Now, the model that we use is actually a network constructed from X-ray CT scans of Bentheimer sandstone. You can see here is a snapshot of the network with porosity and permeability of these values. And then we modeled the mechanisms that I earlier explained, and these are just some results from the pore network modeling. And to compare the results, first of all, we did a kind of analysis against the depletion rate, which is the pressure over time. So we would have, it's a kind of measure that, for instance, you can say how much pressure is being declined per day. And we plotted those data against the mobilization saturation here. First of all, as we can see here, there is no significant change as the pressure depletion is increasing. And that means the higher expansion rate at higher depletion rate is not really controlling the gas mobilization phenomena in this context. And what is important is actually the diffusion, which is really happening at a faster rate at lower depletion rates. And also, we can note that the average mobilization threshold is 0.06, which is really in agreement with our field scale observations, and also the reported values in the literature. Of course, in the context of oil and gas industry, but still, it is kind of, in agreement. And the other part, which is really the interesting part, in my opinion, is the behavior of remobilized gas. In this case, because some people are say that the geological CO2 is the hype. You cannot store the CO2, but you always worry about that if it gets mobile, if it gets gets its way to the atmosphere, then what happens? We are wasting money and time and everything. But actually, this tells us that even though the CO2, the trapped CO2, can become mobile at some point, but the relative permeability of water, the relative permeability of CO2, of the remobilized CO2, is very much reduced compared to the drainage relative permeability and also to the imbibition relative permeability. So this is good news in the context of CO2 storage because, even though CO2 can become mobile, but it is not that much mobile, so to speak. And this is really interesting. Also, we tried with different depletion rates here as well, but because we didn't see any difference, so I'm just plotting one figure here for demonstration. And this blue line here is the primary drainage, and then we have the imbibition curve, and then we have the secondary drainage, which is now driven by the pressure decline. We could also have secondary drainage not driven by the depletion. That would be a different story, and we may immediately see that the CO2 gets mobile and moves at a faster rate. But here we are specifically talking about the depletion scenario, where the CO2 becomes mobile as a result of depletion, not as a result of injection. So that's very important to note. And if you wonder about why we have such a behavior here, it's because of a strongly water-red assumption that we did here. But of course, I mean, this has also been seen at the lab scale. So if I want to explain this phenomena, because we are most of the time we are kind of familiar with these curves that are, and the imbibition is usually smaller than the drainage, or it's below the drainage curve. But in this case, because the assumption is that strongly water-red, so at the end of the drainage process, we would have essentially a lot of dead-end pore CO2 filled pores. And as a result, pore filling is more favored at the beginning of the imbibition than a snap off. So we would have a sharp, or we would have a decrease in the gas saturation, but not that much in the relative permeability. So that's why we are observing such behavior here. But also, if you note here, near to the residual gas saturation, we would have a sharp decrease. This is also a characteristic of a strongly water-red systems. And to read more, I would highly recommend to reach out to this paper by Spitter et al. 2005. So I was actually going to explain a little bit more, but I was not really sure how much time do I have. But if I have some time, I can just show the other slides as well. But the conclusion so far here is that the remobilization of gas in the context of CO2 storage is most likely to be governed by the diffusion rather than by expansion. And under the depletion conditions, the gas relative permeability, or better to say the remobilized gas relative permeability, increases very slowly, which is a good news, as I said, even beyond saturations, beyond saturations of critical gas saturation. And so this means that the residual trapping is indeed safe, and the geological CO2 storage is actually not a hype, and we can really trust in residual trapping and geological CO2 storage as a way to mitigate climate changes. And we don't really need to worry about the security of residual trapping in long terms. So, and then these are the key references, specifically the special edition, which is available in International Journal of Greenhouse Gas Control, which is focused on the pellet CO2 injection experiments. And the other papers, specifically the latest one, which talks about the rule of critical gas saturation in the field-scale CO2 injection experiments. And the final slide. This is just a quote I found in the internet. So everything turns into Pore media. So thank you very much for listening. And I'm ready for questions.
Thank you, Ramin. Thank you for this interesting talk.
I just go to this because I can see you, so I can,
Okay. It was really interesting. both observation from the field and also from the insight that you provided based on the modeling and interpretations. I have a question of my own before we receive question from the comments. As you know, there are two different strategies for CO2 storage: either store CO2 in a structural trap, or put the CO2 in a hydrodynamic layer and then store CO2 in that sense. Do you think, is there any difference in terms of remobilization based on these two scenarios? And also, do we have any knowledge about the phase state of CO2 when it becomes remobilized inside the porous medium? Is it still in supercritical phase, or it will change properties?
Well, a great question. First of all, I mean, in the Pore-scale modelings that I am conducting right now, we are really taking into account the gas phase, if there is any changes in the gas phase properties. So it's a dynamic Pore-scale modeling. But still, we keep the conditions so that the CO2 always at the supercritical conditions. But probably, if the depletion rate is so high, we may have some significant changes in the gas properties, which really needs to be taken into account when modeling gas remobilization. But about the first question, I don't think there would be a great difference, because what we are talking about is a depletion scenario. So, I mean, it doesn't matter actually in which condition it happens, as long as we are really in a depletion scenario where the pressure is declining and the gas is remobilized due to the pressure decline, then we would probably see kind of, very similar effects in terms of the relative permeability function specifically. But but would be interesting at least to try and see if, different, aquifer condition would have a significant effect or not. Yeah, that's a good point actually to try out.
Okay, great, thank you. We have one comment from Martin. Ed and Ramin, two great talks. Thank you, Martin, for your support. We have one question from Sina Momeni. Thank you, Ramin, well done. Do you consider gas diffusion coefficient as a constant or a function of gas saturation function?
Well, both indeed, but the great question indeed. Thanks, Sina. But yes, so we take into account the gas diffusion changes with the gas fraction and also as a function of pressure. But we can also take in, we can also keep it constant because, the diffusion does not really, the diffusion coefficient may not have that much effect. But in the Pore-scale modeling that I'm conducting, yes, it's a dynamic Pore-scale modeling, so everything is pressure dependent. So the only thing that we keep it constant is the temperature, and the rest is just being updated all the time as the pressure is declining.
Great.
Yeah.
Another comment from Ahmed Rizk, one of our previous speakers from Khalifa University. Thank you for interesting talks. Yeah, it seems that we don't have another question from the audience. I would like to thank you, Ramin, for this wonderful talk, and also thank Ed for very interesting insights into the role of topology when we are dealing with low salinity water injection. With that, I would like to move on to our next slide. In 2 weeks, we don't have any Porous Media Tea Time Talks webinar scheduled because of the next Interpore annual meeting, Interpore 2022. It's a hybrid conference. The physical part is in Khalifa University in Abu Dhabi, and also you can join the conference as a hybrid conference. So don't say, you can go to a registration, and also you can follow the whole conference in-house when you are at home, and if you cannot travel there. With that, I would like to thank you all for today. Thank you for comments, for your support. This is the Porous Media Tea Time Talks team. We are a team of 8 different researchers from different universities, and we always welcome your comments and criticisms. And if you want to come and talk about your research, please contact us at porous-media-ttt@gmail.com. With that, I would like to thank you all and wish you a very lovely afternoon. Bye-bye, everyone.
Bye bye.